I watched a lot of them. Lester or Lester.
I see you were right.
Yes, yes, I'm just watching.
Chairs up here.
Yes, I'm watching something like this.
Yeah. Good job, thank you. Class time, class time. All right, so this is going to be, as usual, completely different. So our speaker tonight is going to be using his computer and his projector and this great big screen, so we're all going to get completely spoiled. At our next meeting, we'll be looking at the little TV and going, but that's so small. So this will be nice. But when he's done, and we have the usual questions and answer stuff, then we're going to take this all down and we're going to switch everything back to the normal setup. So people on Zoom, be patient while we work everything up. And so now, as usual, Barb will come up and do her usual introductory thing and mention things like, thank you to the Cold Creek Canyon Park and Rec for sponsoring us. Okay.
I hear something back.
Something's in the back. Well, George wants to listen.
Yeah.
With headphones.
I guess.
All righty,
Okay,
you're up, Barb.
so thank you for coming tonight and for also the people on Zoom. And let me pass around some April. Judy gave me a bad time for giving the one last month that was just a couple weeks, so this is next one. Oh, good, April, oh, right. And I don't think we'll be able to see it, but at 9:03 tonight, the space station is supposed to be flying over in this direction, but with the clouds, I don't think we're gonna see it. But if you don't know about how to see the space station, it's spotthestation.nasa.gov, and I'll leave this back there in case you want to get that. So we are thrilled to have Angel, let's say it right, okay, here tonight, and Leonard and I know him really well because we have gone to his conference at Colorado School of Mines, the Space Resources Roundtable, for about 10 or 15 years, something like that. And it's so inspiring, and we just wanted him to come here and share this with you. Also, I wanted to say, he's going to speak first, and then we have a number of people who are going to share information, slides, and amazing aurora pictures from Clark and Y, who aren't here, but John Williams will pull those up, and then they'll be able to talk to us a bit about that. They went to Norway, northern Norway, and saw the auroras, and ice sculptures and all sorts of things. Anyway, then our next meeting will probably be May 3rd, and we have Andy Aldrin, Buzz Aldrin's son, who's committed to come and talk to us. And that will be sort of general about space and commercial space. And he's a really good speaker too. I think you'll really enjoy it. So let's see. Do you want me to, introduce? Okay. So do you want to talk a bit about yourself, or do you want me to?
Go ahead. Just say that I'm
Yeah.
resources at school.
Yeah, School of Mines. And we did have, if you were here, I think it was about a year ago, last December, one of his students, Anastasia Stepanova, was here and gave a talk about her. She wants to be an astronaut, and some of the training she's gone through in isolation and simulated missions. And they also have a really nice sandbox down there. It's with lunar soil. Leonard and I actually haven't seen it yet, but for his June conference, we'll be down there. And I think I'll just turn it over to you to, explain all about these space resources. And we've got people who'll say, why is this important? Why is this important?
Very good.
I know Lena's gonna answer.
Thank you so much, Barb. I really appreciate your introduction and the unique opportunity to be at this beautiful place of Cold Creek Canyon and be able to interact with the SkyWatchers here. I was so excited to come that I decided to, look, I'm going to take the road from where I live, which is downstream of Cold Creek Canyon in Louisville. And I decided to come along the creek all the way up and then all the way up to get into here. So it was a fantastic ride, beautiful. And what would be my surprise that coming up the creek, I saw this sign welcoming me for the 1920x1080 SkyWatchers. That was fantastic. I had to stop. This is fantastic. It was beautiful. The sun was there. It was great. At this place where I'm sure when you go out, you get to enjoy this beautiful, beautiful night sky, packed with stars, especially in the wintertime. And especially now, today, if we had had the chance, weather permitting, we would have seen exactly this view around 9:30, which is the time at which we would have gone out and take a look at it. And what we would have seen, probably you're so familiar with winter sky, we would have seen some visitors, some wanderers, some planets. We have two of them that you can see with your naked eye. You got Mars and you got Jupiter. And then probably with a small telescope, you can see Uranus. So that would be fantastic. But as you can see, they're right there surrounded by some of the brightest stars in the night sky. Let's take a look at them. And they're in the asterism called they call it the winter circle or the winter hexagon, because you can form an hexagon with different sides and the different sides are connected with those bright stars. So let's take a look at some of them. We got, for example, Pollux, one of the twins on the constellation Gemini. That's where we start. Then we go to Capella in the constellation Auriga, which is the charioteer. Then we have the eye of the bull, Aldebaran on Taurus, which is my zodiacal sign. Then we go to Rigel, which is in one of the feet of Orion, which is beautiful these nights. Then we have the brightest star in the sky, Sirius, with the big dog. And even the small little puppy contributes, the Canis Magnus with Procyon. And so if we were out, we would actually be able to see the beautiful hexagon there. But I think it may or may not be possible, who knows? But the thing is, no matter what, when you're here in Cold Creek Canyon, you get to enjoy this beautiful night sky. And I'm sure all of you are enamored with it. And you're also very fond of learning about exploration of the heavens. How is that we can get to these places either by telescopes or spacecraft. And so I also love astronomy and all those types of things. But I'm here tonight to give you a different perspective of space. I'm here to see how is that we can look at space, not just because of its beauty or the mysteries that it holds, but because of the value that it represents for the future of humankind and for future space exploration. So I'm here to talk about the topic of resources beyond Earth and how they will allow us to enhance exploration, to do more than we have been doing in the last 60 years, travel further, larger payloads, be able to stay on planetary bodies. But at the same time, from a practical point of view, how they're going to contribute to what we call now the new space economy. So that will be my topic tonight. So let's get started with a planetary body that all of us are very familiar with, and that is planet Earth, in which natural resources have been the driving force behind exploration, but also the means to do so. They have, and now they're an integral part of our lives, our society, and our economy. They have allowed us to do all sorts of things. And let's see what we can learn from natural resources on Earth as we start looking at resources beyond Earth. So before we go into the future or into space, let's actually go back in time, way, way back. Let's say 120,000 BC. And let's meet our ancestors, the Homo sapiens, at their cradle, their birthplace in southern part of Africa. where as a result of drought and environmental degradation and population growth, they decided to leave to other parts of the continent, to Europe, to Asia, to Oceania, looking for basic survival, water and food. They were not going into a scientific expedition or to see what was on the other side of the mountain or some of these romantic views that we have of our exploration. They were hungry and they were thirsty. And that's what they did. But in the process, and you will see the analogy of what's going to happen in space, they were able to conquer some technologies, how to control fire, how to preserve food, how to come up with tools to live in ever more extreme environment and extreme temperature. Then 15,000 years later, when we crossed into the Americas, it was time for the first economic revolution. That was agriculture that allowed us to finally settle and be able to store food and store energy. 8,000 to 86,000 years ago, we started mining and doing metallurgy, which allow us to now look at resources for different uses, jewelry, religious objects. The first coins that were minted with electrum, which was an alloy of gold and silver in Turkey around 650 BC. Then in the 15th century, when we started venturing to the oceans and we were bold enough to leave, then the driving force behind that was for trade, resources like silk and spices and gold and silver that allow us to then go to some of the most extreme places on the planet. And the search continued in the 19th century, looking for the main source of energy, which is still our main source of energy, which is oil. And the search for resources has continued unabated. In the last 25 or so years, we have been looking for those obscure elements of the periodic table with strange names called the rare earth, which are now fueling our renewable energy industry and our communications industry too. And we continue doing that. In the last 5-10 years, it's been about that third element on the periodic table, lithium, which is now powering the electrical revolution for cars and everything else. So as you can see, resources have allowed us to explore every corner of our planet, to live off the land in ever more extreme environments, and they have become the main engine of our technological society. So what happened when we decided to go beyond the confines of Earth and to explore space? Why did we go out there? Was it resources, survival? In fact, it was a little bit of a survival story. It was the competition between the two superpowers of the day, the Soviet Union and the United States, that wanted to prove their technological superiority. They wanted to gain the higher ground and be able to survive as the best, as the most powerful country on Earth. But even when the race was over, we continue exploring. And we continue doing it mostly for scientific purposes, gathering scientific knowledge. And we have sent probes to every planet of the solar system, asteroids. We have even gone beyond the solar system and we're in interstellar space at this point. But something happened on our way to heaven. We discovered that space had value, that actually could be useful to us. And like any human activity that starts from the point of view of curiosity or science, eventually we find some application that can be useful to humans. To the point that we have become so tied to our space assets that I would tend to say that if we remove our space assets for half an hour, it will bring civilization to its knees. That's how tight we are. And this practicality of space started with the very first telecommunication satellite, private sponsor, Telstar 1 in 1962, that allow us to communicate real time between Europe and the United States. We didn't have to wait for 2 or 3 days to see the soccer match. We could actually see it real time. And what Telstar did was to utilize the first resource from space. And that is simply location, the view from above. This has given us the ability to have weather forecasting, global communications, to pinpoint every point in the surface of the Earth with extreme accuracy, and even monitor the health of our planet as we continue extracting resources. Not only this is the first resource, but it's the only commercial use of space. Telecommunications satellites account for an industry of about $630 billion a year as of 2024, and is predicted to go into the trillions by all sorts of studies. But in order to get to this magnitude of economic growth, we're going to have to use something more than just location. And here we know that we have practically unlimited amount of resources in the solar system and beyond. But here it's important to make a few definitions before I go any further. A resource has value by its utilization. If not, it's just an element of scientific interest or curiosity. It has to have an application in order for an element to be a resource. And there are 3 steps that one needs to follow if you want to extract and utilize resources on Earth, Moon, Mars, or wherever we go. And these are the following. First, you have to have a recoverable resource, which means you know your element with enough geological, but also engineering, but economical, legal, environmental certainty that you know that you can go after it. This is on the mining or the oil and gas industry is what's called a proven reserve. You have to have that certainty. Once you do that, you have to have a technology to recover it. That's going to depend on the environment where you go, or the destination. And third, as important, if not more important, you have to have a customer. If there's no demand, it's not a resource. There's gold in the ocean in parts per billion, but there's no customers for that precious element because it's not economical. So you got to have those 3 things. So what I'm going to do in my presentation, I'm going to go through these 3 steps. First, identify what are these potential resources. What are the technologies that we're developing right now as we plan to recover them? And then look at who are the potential people that are, or organizations that are interested. Now, this topic of space resources or space mining, as some people call it, it may seem to you that it's new. And yes, it's been on the press for quite some time, but it's not new. It's been around for quite some time. This realization of the value of resources goes back, at least from the engineering and scientific point of view, as back as the early 1900s, with Konstantin Tsiolkovsky, which is the grandfather of rocketry. He was the one who he was a high school teacher. And at night, he will go back to home, and he was both a dreamer and a thinker. And he came out with this publication in 1903, The Exploration of Cosmic Space by Means of Reaction Devices, where he was thinking about how that we can escape Earth. And he came out with this beautiful, simple equation called the rocket equation. This is the equation that we still use for every rocket that you see up on the Cape. They're all being governed by that simple equation. And the interesting thing is that he was able to see on that equation the value of space resources. Just thinking about it, I mean, he was quite a mind. I guess he was tired of teaching high school in the morning, and that's why he started looking at those type of things at night. And so what he did, and you don't need to know much math, it's just delta V corresponds to the change in velocity that you have to impart in a rocket to get from one destination to the other. And it's depending on the mass of the rocket. Just let's look at it from that point of view, the propellant that you have. So he solved for mass, and he was able to see that in order to get from one destination to another, the amount of mass of propellant goes exponentially to where you're going. So that really, he light up and he said, this is going to, we may be able to get out from Earth, but it's going to be really hard to travel to long distances. He even talked about it in a science fiction book. If you're science fiction lovers, you got to get this book. It's called Beyond the Planet Earth, published in 1920, where he brings together scientists from all sorts of regions, Newton and Galileo and Kepler and all those. And they're planning this mission to outer space. But on that book, he said the following: there exists a rich and inexhaustible source of material for establishing colonies beyond the Earth orbit. So he was able to see that in order that for us to start putting out even a simple base, live in another planet or the moon, or do things in space, we are going to have to use the material that is available in space. We cannot bring it all from Earth just because of this simple equation. He was quite the thinker. He was doing this in 1903. This is the same year in which we were barely trying to get off the ground with the Wright brothers, and he's already thinking about how is that we can get into space. That's the power of a thinker. And we will see how his dreaming personality also comes through. So, all right, this idea has been around for quite some time. So let's start taking a look at what resources are out there besides location and knowledge. The moment we cross the atmosphere of Earth, we're going to find an environment that is really hard to replicate here on Earth. In space stations, you're going to have ultra high vacuum, you have low gravity, that allows us to make products that may have much better properties than the ones that you can find here on Earth. And in fact, this is happening as we speak. There's companies right now, a company called Made in Space that now is part of another company called Redwire, that is actually building very high quality fiber optics that are much better quality, much better bandwidth that you can find here on Earth. Just last month, a company that is trying to use what's called bioprinting, use 3D printing of bone implants or implants for this one, for example, for problems with the nervous system and the like. And they may even, who knows, in the future may even make organs out of this if you happen to be on Mars or somewhere else. So this is the value of these properties on low Earth orbit. Then we have solar energy, unlimited one, photons, that can serve, yes, to power spacecraft. But think what we can do. If we could capture this energy in orbit and be able to collect it in hundreds of collectors, beam it down to Earth in microwaves, so that they can be collected in rectennas. This is called space-based solar power, 24/7, without worrying about clouds or anything else. It's such an important component that has been around for 40 years on an idea, but now it's starting to make some sense. In fact, Europe, once Ukraine was invaded and they started having problems with oil and all that, they started saying, well, what's going to be part of our 2050 net zero strategy? And space-based solar power was included. You can see that in several plans in Germany and UK, in which they're considering this as part of the net zero study to probably even a 50%, if by that time we can be, we're able to do this in an economic way. In fact, it's so important that China launched the first journal on space solar power and wireless transmission about 2 years ago. And China is already testing the systems, collecting the energy, and also testing the conversion into microwave. So this is an important part. And these are just the intangible resources. People talk about space mining. Remember, it's not just mining. These things, you don't even mine it, but they're resources. Anything that is useful outside, even recycling, is an important part. So these are just intangible resources. Now, to extract and utilize resources more concretely, we're going to have to start traveling. So fasten your seatbelts because we're going to go into a little bit of a trip to destinations to look for resources. So let's start with going to our nearest celestial neighbor. Let's go to our moon. The moon that when we got there in the late 1960s, there was not much that was identified as of use. In fact, if you listen to the recording of the second man on the moon, when he stepped out of the moon or landed, he looked around and he called this magnificent desolation. This is a simple phrase that captures this duality of looking at space from the point of view of science, of beauty, and the other one from practicality. Yes, it's magnificent, and you can see actually our planet from there, but from the practical point of view, it was desolation. No oxygen to breathe, no water to drink, no food, no cows, no wood, nothing that could be of use to us. But this view of the moon has changed radically since then, because we have had, first of all, several spacecraft going around doing what's called remote sensing, being able to sense from the distance what could be potential elements of interest. We actually have material from the moon that we brought with different missions. The Apollo missions were able to bring up to 382 kilograms. The Luna missions from the Soviets, robotically, they brought a little bit, but from different locations. The Chinese were able to bring about 1.7 kilograms from another interesting region of the moon that we're going to talk about. And even from the far side, just recently, they brought a couple of kilograms. So now we have a much better idea of what potential resources can be on the moon that have turned magnificent desolation into a place that could have very important elements for a variety of applications. And so let's take a look at what those elements could be. Now, in order to understand this, we have to understand a little bit about the formation of the moon and the geological process that gave rise to these resources. The most accepted theory at this point, or hypothesis, is that the moon was created with a large impact. This Mars-like planet called Theia impacted the Earth at a very high impact, and material from that planet and from the moon just combined and expel all these materials that then accreted and formed the moon. This molten ball of lava that later on became the moon. And there you can see how this material came out, but then what happened afterwards is what's going to tell us how these resources are distributed geologically. So I can, there's probably a whole course in terms of how the moon evolved, but what I'm going to do is I'm going to shrink 4.5 billion years of geological evolution into 1 minute. Okay, so turn off your phones. Don't go to the restroom. Don't start testing anybody because you're gonna miss millions of years. Okay. All right. So we're gonna start with a moon that is a molten ball of lava. All right. And then we're gonna see how this evolves in 4.5 billion years in just 1 minute. So here we go. We have a molten ball of lava that starts crystallizing and it forms the crust, a very thin crust. And now you have a very smooth, nice surface, beautiful, intact. And then, boom, it gets hit by a large asteroid that forms the South Pole Aitken Basin, one of the largest impact craters in the solar system. And then you have a period of what's called heavy bombardment. You have this asteroid hitting the moon in several parts and forming these big impact craters that break the crust. And with that, you have material that starts coming out on a period of volcanism. And now this lava starts filling these impact craters, and you start seeing the dark spots where you can see the man on the moon or the rabbit. And it's still smooth, but then there's a second period of impact that now starts poking the moon in every place. And then about a billion years go by and nothing happens. And it turns out to be the moon that we see tonight in the night sky. This is our moon. And these are the most important processes. Remember that big impact crater, that you have the large heavy bombardment period, and finally the intermediate bombardment period. And that's going to explain where the resources are on the moon. So what happened after 4.5 billion years? We have two sides of the moon, the near side and the far side. Now remember, all of you here, from what I gathered, are experts, but if you don't know much about the moon, remember it's the far side. It's not the dark side of the moon. I can guarantee you that it's enough light in both places 2 weeks at a time. And the reason for that is because of this very unique property of the moon. Let's say that's the sun right there. This is the Earth. This is the moon. The moon rotates 1 revolution per month, around 28 days. But that revolution corresponds also to a revolution around the Earth. So at the same time that this one is rotating, and we're seeing here the near side of the moon with plenty of light, this is the far side, or people call it the dark side, but let's see if it's dark. It starts rotating, and as you can see, there's plenty of light here, even though we don't see it, but we always see this side of the moon. So yes, we only see that one, but it's the far side, not the dark side. So we may think it's the dark side because we don't see it. But there's also been some cultural elements that have influenced our thinking. I remember when I was in high school, one of the greatest albums from the greatest rock bands, Pink Floyd, came out. If you have not listened to that album, and we have some young people in the room, please listen to it. It's fantastic. The problem is that this thing stuck on my mind, the dark side of the moon. And so it took a while. Then there was novels and all sorts of things talking about the dark side of the moon, and that was a problem. But remember, it's the far side. Okay, because the near side is the one that we see, the one we have communications, is where most of the exploration has happened. You have Apollo, you have China, you have the Soviet Union, the Indians landed on the South Pole just a couple of years ago. Then we started having others, Japan, very close to Apollo 11. Then commercial companies started attempting to do the same thing. And we have intuitive machines, both IM-1 and the one from a few weeks ago, IM-2, that sort of landed on the South Pole. They made an intent. But then we had the very first successful landing of a spacecraft near Mare Crisium, which is the Blue Ghost from Firefly. That hopefully, I'm sure all of you were able to see the beautiful images and the light, but just for the heck of it, let's actually watch the last few moments of the landing of Firefly on the surface of the moon. So what you're gonna see is the surface of the moon.
Khan, Chief Engineer on Ops. Y'all select the landing. We're on the moon.
You've got a company with a meager budget where only big space agencies could do that before, and landing several payloads, one of them from one of your members right here that operated on the moon. Let's give him a round of applause. And functioning nicely. This is an incredible achievement, and I cannot tell you how excited we are about that. And I get carried away, so let me just keep going because this is fantastic. Bob Green. Yes, another round of applause. Yeah, hopefully he can come back at some point and tell us exactly what he found, because he's listening and looking.
We're listening inside the moon.
Inside the moon, way inside of the room. So that's a fantastic achievement. So this is where we are. The far side has been a little bit forgotten because it's hard to get there. You don't see it. There's no communications. But the Chinese have landed there, and not once, but twice, and landed on a region. Remember that big impact at the beginning of the moon, the South Pole Aitken Basin? Because that's one of the most interesting regions scientifically, because that's where a material was exposed. But as you will see, it's also an important region for resources. So the Chinese know how to do things. They land on areas of large scientific interest, but they're going to be potential of use in the future. And they were able to not just have a lander, they have a rover, and they were able to show us the first beautiful panoramic view of an area that we're never going to be able to see with our own eyes unless we're there. That's the far side of the moon. And so this is where we stand at this point in terms of the near side and the far. So now let's start looking at potential resources. Let's first take a look at the ones that are common to both the near side and the far side. One of them, believe it or not, even though the moon doesn't have an atmosphere, it's got plenty of oxygen. 45% of the moon is oxygen. Where is the oxygen?
Water?
Where?
Water? Is it in the water?
Is
the regolith an oxide?
The regolith, it's an oxide. It's oxidized. Very good. Very good. That's where it is. So you just have to heat it up and the oxygen will come out. We also have plenty of silicon, which is great for the semiconductor industry, but that's where the commonalities end in terms of the elements being on both sides. For other elements, we're going to have to start looking at some of the geological features and how it evolved. I'm not going to get into details. Let me just talk about the main features that you can see with your own eyes right there. One, there's a region called the Maria. That dark spots, the rabbit on the moon, the man on the moon. It was called like that by Kepler because Maria is in Latin seas. He thought there were oceans. He was sort of right, because at some point there were oceans of lava there, so not bad. And this is where you have volcanic material, basaltic material. The rest, about 83% of the moon, is what's called the terra, the highlands. This is the primordial crust of the moon that's been there for billions of years, just exposed to all this erosion by asteroids, northocetic material. And this is where you start seeing the differences between the two in terms of resources. For example, iron, that is so important for all of our industry here on Earth, mostly concentrated on the near side, on the Maria. But look at the place where the Chinese landed. You know, there's significant amounts of iron right there, so not a bad place to land. Titanium, that is important for the aerospace industry, also highly concentrated on the near side with a few spots on the South Pole Aitken Basin. Now, the moon has this creepy side to it. Creep with a K. that stands for potassium, rare earth, and phosphorus, which are also very important elements. This is a region that remained liquid while the rest of the moon was crystallizing, because also it has some radioactive material. It has uranium and thorium. In fact, this is a map of thorium, and that locates that region. And in fact, this is the other region where the Chinese landed and where they got material and brought it to Earth. So again, very important and strategic places where to go. Now, if you're in the mining business, once you identify potential elements, the first thing you have to do is to crash the rock. You have to drill, blast it so that you can pulverize it and then be able to extract the material. Luckily, nature has done some work for us already, because the moon has been bombarded for billions of years. First, comets, asteroids, meteorites, micrometeorites, and in the process, these rocks, when they have impacted the surface of the moon, what they have done is crushed the bedrock that existed and can completely pulverize the material. So that what we have now is this very fine dust all over the surface of the moon. And this is what's called the lunar regolith. It's this superficial material that you find on the moon. And that's why you see the footprints of the astronauts on the moon. You don't see them walking on rocks. You see them working on this very fine dust that has been produced over billions of years of being bombarded. It has an average particle size of about 70 microns, so it's extremely fine. And it's in the uppermost 10 meters or so, has been accumulated by a process called gardening. You garden it, but with micrometeorites. And so you have all this fine material. Now, this is the material that actually is so important that this is where we're going to find the most important resources. This is the material that's ready to go. It's fine, and you can start processing it. Although it's a little bit different from what we find on Earth. This is terrestrial sand. This is sand that you can get up to in Cold Creek right here. Nicely rounded pebbles, erosion by water and by wind. Totally different from what you find on the moon, which you can see this glassy material, this material with jagged edges, extremely abrasive agglutinates that we're going to have to deal with them because they're going to eat up any machinery that you have. If you ingest this, your lungs are going to be torn apart completely. So you're going to have to watch out. So it's very different, but this is the material that we have. Now, the moon has been not only been bombarded by micrometeorites and asteroids and the like, but also has been bombarded by solar wind. These are particles that come from eruptions from the sun, and because the moon doesn't have a magnetic field, they just get implanted on the surface of the moon. We don't have that on Earth because we have a magnetic field. So in fact, this lethal radiation that comes from Earth, we actually look at it from a very romantic point of view. You can see the aurora borealis, and somebody's going to talk about this. Beautiful greens and reds. What this couple doesn't know is that we didn't have a magnetic field, they will be fried in an instant. So something to think about when we start thinking about having a base or a settlement on the moon, where you're going to have lots of these radiation. But this radiation is good for other things. It has implanted, the moon has its own resources, but it has implanted volatiles in there. And some of them quite important: hydrogen, helium, nitrogen, carbon. These may be only the few sources of carbon and nitrogen that we have on the moon. There has been also an element that has been identified that exists in larger amounts on the moon than on Earth. And I was talking to Bob Green today about that. And that is helium-3. It's an isotope of helium. Just remove one of the neutrons and you got this thing. That started causing attention after Apollo 17 by astronaut Harrison Smith that said, this is a really good source of fusion energy. Not fission, but fusion, which means you can have two particles of helium-3, you bring them together, they generate electricity directed with protons, and the waste is helium, non-radioactive. This is stuff that you can breathe and talk funny or use it for balloons, but it's clean. Now, it caught a lot of attention and a lot of fuss, fusion, yeah. But then disappear a little bit. And then new technology came about to the point that now people are already looking again to helium-3. Why? Because they're using quantum computing medical equipment, defense applications. So there are two companies now that are looking about going about helium-3, but still fusion is not been invented. Look at the amounts, parts per billion. This is a tiny little nothing of helium-3. So you're gonna have to mine or extract a lot of material in order to get reasonable amounts. But who knows? People are talking about quantum computing centers on the moon where you can have extreme temperatures. So the future will tell us what's happening. Other resources on the moon. Location. How about lava tubes? Lava tubes on Earth are these geological features where lava flowed and then the upper part solidified and you form these tubes. Same thing got found on the moon. You can see here where lava flowed at some point, and then the roof was exposed, or the roof of this part, by impacts from asteroids that allow us to see inside these places that can become a place where you can store equipment or even have humans down there at a reasonable average temperature. So location, it's important. We may actually go back to the caves when we actually go to the moon, but you got to start somewhere. All right. How about that element that we always look for wherever we go as humans? What water? Well, there was not much hope to find water on the moon because the moon has this interesting property that is tilted just 1.5 degrees towards the sun, not 23 degrees that we have here on Earth. So in a typical day and night cycle on the moon, all the face of the moon is exposed. So any hope that water could be in the surface and have it there as a gas or liquid literally evaporates. But this brings up a point that the rays of the sun are so obliques on the poles. In fact, if you're in the South Pole, where everybody wants to have a base, psychologically, it will be a very depressing place to be because you're seeing the sun up and down. It's the sunrise, sundown. Do I go to bed? Do I wake up? Long shadow. But that's where we want to go, and we'll see why. So scientists started thinking, well, if we have those oblique regions, could it be that we have these very deep craters that have never, ever seen the light of the sun for billions of years that can store water coming from comets or asteroids that are going to these regions that are extremely cold? We're talking about 40-degree Kelvin of that. Like, let's take a look at one of them, for example. This is a typical day and night cycle. Let's check this out, for example. It has some light, but this part here is completely in the darkness. It doesn't matter, goes up round and around and around. So there may be a possibility that water ice is there. So several missions were sent to check this out and look at this very, this happens to be the South Pole. So there were different missions, Clementine in 1994, Lunar Prospector in 1999, the Indians with an infrared spectrometer, and the Lunar Reconnaissance Orbiter. They carried different spectrometers, neutron spectrometers, in which they got signals. They were able to see signals of water or hydrogen or OH radical, something that looked like water. So this is remote sensing, mind you. But the signals were strong enough that they say, we might as well look to see if that's the case. Now, what these missions were able to give us, first of all, is to find another important element again, which is location. And so they were able to find that indeed, both in the South Pole and the North Pole, you have these permanently shallow regions, or PSRs. But as important as these dark places are the rims of these craters that were named a very romantic and poetic thing called Peak of Eternal Light. This was a French scientist, Flammarion, that called it, it's going to be light forever. Well, not necessarily, but about 93% of the time you have light. You don't have to wait for 2 weeks of darkness and 2 weeks of light. You have plenty of light, you have power, you have communications with Earth. And that is why you see all these countries, the US and China and US and the Indians, and everybody wants to have a base on the moon because they want to be on those high peaks. So real estate becomes very important here. Yes, the moon is big, but these are prime real estate, and that's where we want to go. And these are places that we will see later in which not only we can have communications and power, but we can beam down that energy and maybe use that to extract some of the water that is there. I'm going to explain that later. All right. So these were some of the signals that came out from all this is a neutron count of potential of hydrogen. So the idea was, all right, we're seeing this from a distance. How about just going there and touching it? Geologists and mining people want to go and touch to see if the real thing is there. So that's what we did, exactly. So they looked at where is the most stronger signals coming? Let's see, Cabellos. All right, let's go and hit Cabellos and let's see what happens. And so this mission called L-Cross did exactly that. This mission, the mission that sent the Lunar Reconnaissance Orbiter, then later on, the upper stage separated that white one from the second one, and it was sent to Cabellos at the highest speed possible, kilometers per second. And it hit it so hard that a plume came out. You can see here this cloud in which the second spacecraft was able to see in there and was able to determine that indeed there was some content of water, anywhere from 3 to 8%. And not just water, all sorts of different materials that that could be bad because there could be contaminants. If you want to drink this water, well, your breath is not going to be very nice with hydrogen sulfide. Then you got mercury, you got magnesium, you got ammonia. But look at it from the point of view of resources. These may be great sources of nitrogen, of carbon, if you want to do methane or whatever you want to do. So it cuts both ways. But we need to go inside and do more work. This is the only data point that we have, which is not enough. So what we have right now, the view is that indeed in these permanently shallow regions, let's take a look at the South Pole, there exists some water ice that has been detected in this region, which is, let's call it the Arctic circle of the moon, that may be of potential use. But again, this is from remote sensing and one data point. But that has not stopped engineers and scientists and commercial companies to try to estimate how much water there is. So the estimate right now is that it's about 100 million to 1 billion metric tons of water. 1 billion metric tons of water. Whoa. What is that? Is that an Atlantic Ocean, a Pacific Ocean, a lake? Any guess?
One of the
Swimming
great lakes.
pools full.
Lake Superior.
One of the lakes, but the tiniest lakes of all, the Lake St. Clair. That's the amount of water that you have on the moon. And actually, let's put it in Colorado water measurements. It's about 2 to 3 Lake Dillons. So you would say, well, that's not much water. But remember, if you're thinking about water for humans, humans can recycle up to 95%. We're doing that on the space station. So that's not an issue. But how about water that we can split into hydrogen and oxygen, and that can give us fuel? If we do that, and you make the calculation, that will be enough hydrogen and oxygen to fuel one shuttle launch per day for the next 2,200 years. So not bad. Now, mind you, these are rough estimates, and you're going to use it all, which is really hard. But at least tells you there's a possibility that we can use this for propellant and use it not only on the moon, but somewhere else, as we will see in a moment. So this is where we stand. So these are the elements that we have on the moon. You got metals, rare earths, volatiles, and the like. But let's keep going. Let's not stop on the moon. Let's actually catch up with these amorphous rocks that are floating all over the solar system, the asteroids, that fluctuate from anywhere about a meter to even kilometers series, which is a dwarf planet. As you can see, you go from this irregularly shaped more and more towards a more spherical one as your gravity starts going up and you start becoming more of a planet. But most of them are those small rocks. And these are the rocks that probably you learned in high school that they're very well behaved. They're in a belt between Mars and Jupiter, but nature doesn't behave that way. Sometimes there are impacts, there's resonance, and they end up all over the solar system. You may see the skies as peaceful, there are rocks all over the place. And some of them are trapped in orbits very close to the one that the sun has around the sun, the Earth has around the sun. So this is the Earth going around the sun, and all these dots are what's called near-Earth objects that are trapped asteroids there. That they're interesting because they're closer to the main belt. So why not go there to extract their resource? So let's take a look at the potential resources on asteroids. And this is how they're classified. People that are in the asteroid science, they have a classification of like 30 of them. But from the point of view of resources, I'm going to mention just 3 important ones. And this is the spectrum. These are the way that we have characterized them from observatories from the ground or orbital. And these are the 3 important types. You got the type C, called C because carbonaceous. And this is for Bennu. As you know, we actually went there and we have a sample from Bennu, from the Osiris recognition. So they have carbon, but also they have up to 20% water. And these are some of the findings actually that were found on not just Bennu, but Ryugu. The S types, like Irokawa, that these are the stony objects in which you start seeing some important metals, nickel and iron. And then you have the metallic types that we have not visited. There's a mission right now called Psyche that is going, this is what we know about Psyche now. And it's going to go there. And now you start seeing things like noble metals, the platinum group metals, platinum, rhodium, iridium. And these are some of the important elements. So these are the 3 important classifications from the point of view of resource. Now, when you leave today, you're going to say, I don't remember much of what he said. And I don't remember the classifications. What letters did he use? I'm going to give you a tip. Very simple. And you will remember it forever. CSM, Colorado School of Mine. You know, it's a shameless plug and advertising, but I still bump into students 50 years from now, and I tell them, do you remember the asteroid type? Oh yeah, Colorado School of Mines. Yes. So they may not know what they are anymore, but that's what they are. And so we know about them from spectral observations, but we also have this thing called meteorites, more than 55,000 that have fallen into our hands. That the way, and some of them come from asteroids, and we may not know exactly where they come from, but we know what they are made of. And in fact, I brought here one of the heaviest rockets that you can hold in your hand. This is a metallic type, or actually, they have a different classification: stony iron. This is an iron meteorite. And then I have another one, which is one of the most interesting meteorites that you can find. It's a stony type. It's called the Allende meteorite. One of the most famous and most studied ones is one of the oldest pieces that we have in our hands. If you want to have antiques in your home, this is it. 4.5 billion years. This is formed with material that was dust in our solar system. Some of the first metals, aluminum and calcium, you can see inclusions there. And this is a fantastic piece of material, which is that one over there, which I know is real and authentic because I picked it up myself, because I was born very close to where this thing fell in 1969, February 1st, which was at the time in which NASA was ready with chambers to look at the lunar samples. And that's why they studied this to death. And so you're welcome to see it later on. All right. So we have the intangible resources. We have the resources from the moon, all sorts of things, metals, rare earth, and volatiles, water. We have the 3 different types of asteroids, type C, SM, now that you know. Let's keep going a little bit more, at least in what we see that may be a place where we can extract and utilize resources in the next 30 to 40 years. So let's go to the red planet. And there was somebody from Cheap FPL here. There you go. There you go. JPL has been probably actually we know more about Mars than we know about the moon. Because we have all these spacecraft that have been going around gathering remote sensing. We have rovers on all sorts of places that have allowed us to look at what Mars is made on the surface. And what we have found is that, like any body in the solar system, we're made of the same stuff. It's just that different geological processes accumulate this material. So yes, we have all the metals and the non-metals that we find on the moon. But the interesting thing about Mars is water. Water that you can even see from here. I mean, there's water in the North Pole, the South Pole, combined probably with some carbon dioxide, but it's right there for the taking. You don't have to go to these permanently shallow regions. You can see them. I mean, there's this European Space Agency that there's snow inside one of these craters called the Korolev crater. The mission that we sent, Phoenix Lander, just barely scraped the surface, and you can find their water ice a few centimeters below there. Great. But this is, if we're going to have at some point humans on Mars, this is not great places to live. This is like going to the Arctic or Antarctica, cold, dark. So the consensus now in terms of scientists and engineers is that if you're going to have a humans on Mars, it's going to be somewhere around 50 south and 50 north. These is our places where it's more benign for people to live. And if you look and compare these to Earth, makes sense. 50 north, it's like living in North Dakota. People live there, so why not? 50 south, it's just living in the bottom of Argentina and Chile, the Patagonia, people live there, why not? So that's a good place. So where can we find water on these places? I mean, it's not obvious, it's not there, but if you're around the 40-degree north or the 40-degree south, you can actually find water right below the surface. This is an actual enhanced visible image of a spacecraft flying by and seeing glaciers of ice a few meters below the surface around 40-degree north and south. Plenty of water there. If you want to live more in the equator, then water can come from what's called hydrated minerals. These are water that is locked in the minerals up to 20%. For example, it's gypsum that can have up to 20%, or something that is very common in Colorado, clays, can have up to 4% or so of water. And if you're really thirsty, you can just pick up Martian regolith, and you got 1 to 2% of water. You're gonna have to heat it up a little bit more than the others, but it can come out. Now, Mars also has an atmosphere, very thin, but it has plenty of carbon dioxide. And once you have carbon, think about methane, ethylene, and hydrocarbons, and plastics, and everything that we do with carbon. So that's an important part. And let's not forget about its moon, Phobos, and Deimos that are hypothesized that they may be captured asteroids that may have some of the same component as Type C asteroid. So there you have it. These are the different resources that we have found in the neighborhood. I'm not going to talk about Titan or Europa. That's a little bit far out. But these are just natural resources. Believe it or not, we actually have human-made resources in space. And that's all the junk and all the debris that we have sent for 60 years that is floating around. We have spent a lot of money. Why just let it burn in the atmosphere? Why not recycle the material, the aluminum, the titanium, and use it for structural materials, for propellant? That's what's called recycling, which is actually a resource. So these are all potential resources. So, all right, you're looking at it and you're saying, okay, which space resource is more valuable? Well, let me ask, which space resource do you think is more valuable? And let me give you some examples. Noble, precious metals, oxygen, water, solar power, helium-3, location, space debris. Who goes for noble and precious metal? Nobody's really here. Oh, yeah. Somebody, good.
More valuable to whom?
Very good. Very good. I'm going to go into that. Metals, iron, aluminum, titanium. Somebody that deals with metals all day long. Oxygen.
Yeah.
We need to breathe. Okay. Water.
Yeah.
Very good. People are thirsty. We should give them a little bit of the water part. Solar power. It's getting cold. Yeah, very good. Helium-3. Go with helium-3. Yeah, more or less. Location.
Still like that.
Location. Yeah, even for tourism, that's going to be an important one.
Depending on the location you pick, why use one resource you can get,
Very
when you can
good.
get them all.
Very good. Very good. Space debris. All right. So that's just like the gentleman said, and also back there. This is a tricky question. Like everything, it depends. I didn't tell you if it's in the near term, in the long term, if it's going to be used, to bring back to Earth, or to use in space. So it all depends. If you think about bringing resources to Earth, really doesn't make sense. We have plenty of resources on Earth. We have barely scratched the surface. Maybe in the long term, if we start causing major environmental disaster, a lot of power, too deep, maybe. But it really doesn't make sense. What about using the resources not here, but in space? Think about this. We have sent hundreds or thousands of rockets to space. Every bolt, every nut, every satellite, everything that we have sent to Earth comes to space comes from Earth. We depend 100% from our planet to explore space. And that at some point doesn't make sense. That's not sustainable. Yes, we have achieved a lot by doing this, but at some point it's going to limit what we can do. You look at a payload that goes to Pluto, you have this big rocket, and what you end up sending is just this little instrument because it's very difficult to send things from Earth. Why? Because this thing called gravity. Gravity that keeps us firmly on the ground, that makes it so hard to send things to space and so expensive. Take a look at any rocket on the launch pad. This happens to be the Saturn V that took us to the moon. But I don't care what it is. Could be the Artemis rocket, could be a SpaceX rocket. I don't care what rocket is there. If you look at it, 90% of that rocket is fuel. To send that other 10% with your satellite, with your payload, and you're lucky because this is also takes into account the structure, the pumps. So you can probably, you're lucky to send 2 to 4% of that. That's not an efficient way to send things to space, but that's all we have. And it's not an economical proposition. Even with the largest economy scale, the largest rocket, it costs about $5,000 a kilogram to send something to low Earth orbit. You want to go to the moon? 50,000. You want to go all the way to Mars? $500,000 per kilogram. This bottle was going to cost you about $250,000. So doesn't make much of a sense. And that's just material. You want to save humans, multiply that by 10 because we are a very tough species to keep alive. In fact, I made sure to look this morning because the price of gold has been going up heavily. And I looked at the price of gold, multiply it by my weight, and I am literally worth my weight in gold just to send me to lower orbit. So that is not a good thing. And you're going to say, my gosh, that's an exponential rise in cost. Yes, exponential, because remember our friend Konstantin Tsiolkovsky, his rocket equation, it's an exponential equation. If you want to go from 0.2 to 3, the amount of mass that you want to bring for propellant goes up exponentially to the point that it just doesn't make sense from the point of energy, the point of economics, and the like. So when the question is which space resource is more valuable, it's not about bringing things to Earth. It's about using the resources in space for space. It's the concept of living off the land. Don't bring with you all the propellant. Don't bring your bricks and mortar to make a base on the moon. Don't bring everything from Earth. Use what you have. Look at that. We have plenty of material. Why bring it with us? This is not the way we do it on Earth. Why do it in space? This is, we call it in our field in a very sophisticated way. We call it in situ resource utilization. It's just using resources on site. And so when you start looking at what could be the most important ones, first and foremost, is good old water. Same element that we go after wherever we go. Why water? Not just for drinking or for growing plants or taking showers or protecting yourself against radiation. It's because you can split it into hydrogen and oxygen, which is the most energetic propellant that you can find. So think about what we can do if we now have the capability of having water to use on the moon, hydrogen and oxygen to be propelling from the moon. If you're able to propel yourself from the moon at 1/6 gravity, if you have the infrastructure, it will be cheaper to send the material to where the space station is, which is going to be around 902 today, which is just a few kilometers. It's less expensive than to send it from Earth if you had everything ready. You can also put fuel stations that you can have it for refueling while you start going to places. You can start now using developing a propellant refueling network in space. You can start refueling spent spacecraft and even satellites in geosynchronous orbit. You can even bring water from satellites and putting on depots. And that's when you start developing a water economy in space. And that's just water. Let's use the regolith. It's right there for construction, additive manufacturing. These are plans from the NASA, from ESA. You can make tools, spare parts from the material. Don't carry it with you. If you need a tool, it's a very expensive tool to bring to you. So now that we have seen the potential resources, now let's take a look at technology that is being now developed to recover it. This is technology that is being demonstrated. So when we're ready to extract the resource, we have something to do it. And this is where the concept of space mining comes in. Now remember, space resources is a lot of things. Space mining is how you can extract things. On Earth, we have been very successful mining because we have these huge trucks and everything, because we have four things. We have normal gravity. That's the only gravity that we know. So we have designed things correctly. We know our terrestrial environment, our pressure, our temperature. We have plenty of labor, we have plenty of power. But if we're gonna go to the moon or Mars, none of those things are gonna be the same. Everything is gonna change, so we have to adapt. You're gonna have to adapt to 1/6 gravity, to 1/3 gravity, to no gravity at all in an asteroid. Extreme vacuum, extreme temperatures. Labor, as you can see up there, not much labor, so we're gonna have to go robotically. Power, solar power, maybe nuclear power. We're gonna have to adapt our systems to do this. And so I'm gonna show you a few technologies that we're using in all the different aspects of mining, called the value chain. What is that you do first in mining? Well, you do prospecting. What is prospecting? Exactly what happened here in Colorado in 1859. That's what we started. In fact, this is a picture in the early 1900s of a gentleman panning for gold in Clear Creek. School of Mines is just around there. This is Road 6. And that's the way that gold was discovered. The voice was spread around. Thousands of people came without doing proper exploration. So some of them didn't make it. But that's how we populated our state, because people came looking for gold and silver. That's what we're going to have to do on the moon. And in fact, we're doing that. We were about to do it, in fact, a few weeks ago. And we need to prospect because, yes, we have water ice, but how's that ice on the moon? Is that ready to be shoveled in a crater, 100% water? Is it mixed with a little bit of dirty ice, or is it actually hard packed and 4% of that only with ice regolith, and you're gonna have to drill and it's very hard? We don't know. So we have to do the prospecting. And this started, or was to be started, with the first drill on the South Pole from the Prime 1 mission that went into intuitive machines. That unfortunately fell to one side. The drill worked fine, but it couldn't drill anything. And the idea was the following, and will be tried later. This is intuitive machines trying to land on the moon. If everything would have gone well, this drill, called the Trident, made by Honeybee Robotics, was carried on board. And then this thing called a massive spectrometer. Think about it as an instrument to just look for important elements. And the idea was, you're going to drill in stages. You drill 30 centimeters, then you pull some of this material, and then you have the massive spectrometer looking at it to see what's on that first layer. Then you go down to 60 centimeters, probably having a different type of element, and then you start identifying it. And then go down to a full meter and bring it out, so that then the massive spectrometer can look for those important elements, such as the one that I've been talking about. First and foremost, water, but also hydrogen and carbon dioxide and nitrogen. So that was the purpose of this mission. It may be flown again, but hopefully it had flown in a different type of mission, which is called the Viper mission, Volatile Investigating Polar Exploration Rover, which was canceled last year, but there's hope that it can be revived, because if it does, then you're going to carry on board that Trident drill, but now it can move. It's not just in one location. Now you can go down to the permanently shallow regions. You can drill in different spots to see the distribution, the concentration, and how does it look in different parts, to get a better idea and mapping the prospecting on. Excavation. Now that we know what the material is, let's now excavate it. And this is an example of an instrument that has been developed. Doesn't look like anything that I show you that looks on a mining field, but it's made specifically for the moon. So Racer, what he can do is excavate and transport at the same thing. He can operate at 1/6 gravity. He has enough traction. He doesn't have any lubricants because it's in a pure vacuum. They don't evaporate. They're completely robotic. You can have one or a swarm of this, and once goes wrong, then you can use this one. So this is the excavation system that may be tested in a couple more years on the surface of the moon, and it can also be done on the surface of Mars. So once you excavate, then you have to extract. And here are different concepts, again, adapted for the moon. This is the thermal mining concept. As the word says, you mine with heat. You just redirect the rays from the rings of the crater. The moment the lunar regolith sees light or heat for the first time in billions of years, it's going to start sublimating. It's going to go from a solid to a gas. It can be trapped. or contained in a tent, then in a cold trap that can move back and forth from here to the electrolysis plant, you can extract the material. This is one of the concepts, there's others, but this minimizes the amount of drilling and the like. Then let's go to manufacturing. Let's use the lunar regolith. So lunar regolith sintering, this is a technique in which here we're replicating, concentrating solar power on a lunar simulant. And what you can do is you can not only extract the material, but you can melt it or sinter it. So you can start doing, landing pads or roads or berms, or you can even move it around and do 3D printing of material, just concentrating solar energy on the lunar regolith. And even construction, 3D printed habitats. A company that actually started building homes here on Earth called Icon. It's like 3D printed homes. They can build you a home like this in 48 hours. And they have built entire neighborhoods. They started saying, well, can we do the same thing in space? And they started talking with NASA, and NASA said, you guys have a very forward-thinking approach. Let's test it. And they did this on one of the hangars at NASA. And they used Mars regolith, and they used one of the large 3D printers to build a habitat, simulate a habitat on Mars. So in a few days, they were able to build this whole habitat there, and even put a crew that lived there for a full year and simulated living on Mars in one of these 3D printed homes. So that's the idea behind using the regolith, what you have, and not bring with you the bricks and mortar and be able to do it that way. And speaking of Mars, right now, as we speak, there's this robot called Perseverance that is extracting for the first time the first resource in space. It's ingesting carbon dioxide through a unit called MOXIE, and it's producing oxygen. So there's oxygen on the moon now being produced. If you go to Mars, you can breathe this oxygen for 20 minutes, and then that will be it. But it's a demonstration. It's a demonstration, and the thinking is that if you can scale it up, you have oxygen, and it's being demonstrated. So this is where we are in terms of the technology. But who cares about it? Who is the customer? What is the demand for this? Well, this is interesting because just in the US government, if you had come to us like 50 years ago, the only agency that was interested was NASA, because they could see this, it will lower costs, lower risk, this could use this on the future, but things were moving slowly at that point. But once things started picking up, now it's not just the US government, it's the United States Geological Survey that said we can do natural resources on Earth, why not do it on the moon? And don't trust me, trust Leonard David, which is here in the audience. You know that article, right there. So he knows things, and that's why the USGS, which actually happens to be here in Colorado, is interested. Not only that, the Department of Commerce started thinking, well, if there's going to be commercial applications, we need to have our own space administration within the Department of Commerce. The Department of Energy, that is looking at a space strategy, nuclear power, solar power, fuel cells, even defense. The Department of Defense is looking at how to protect economic assets and even use these for their own purposes, how to move and refuel in space. So you can start seeing all this activity taking place. And by the way, several of these are here in Colorado. So Colorado is playing, from the point of view of the US government, a pretty big role. And not just the government, aerospace companies, starting in 2016 which back then was the largest launch provider, United Launch Alliance. In 2016, this is a key year for space resources because United Launch Alliance says for the first time, I'm going to be a customer. If you can refuel my spacecraft in low Earth orbit so that I can use it for my satellites, I'll take it. I don't care where the water comes from, the moon or asteroids, I'll do it. Then Lockheed Martin followed with the concept of a lunar lander that will be refueled with hydrogen and oxygen, so it can be refueled on the moon. And other companies, Boeing and Northrop Grumman, started talking about, well, how about the fuel depots in space? And not just the traditional aerospace companies. The new space started coming around, SpaceX offering to take us to the moon, to take NASA to the moon, Blue Origin, with a strange concept first, but now that he's teamed up with Lockheed Martin and they're working on a lunar lander. So now you can see all this activity in terms of aerospace companies. And by the way, most of these companies have either headquarters or presence here in Colorado. So we're going, and it's not just the US. Yes, a few years ago it was NASA, but in 2016, one of the smallest countries in the world, Luxembourg, launched an initiative to go after space resources, seeing it from the point of view of financial and commercial point of view. And once this happened, now we have Russia, we have other European countries, we have the Canadians, we have the Indians, we have the Japanese and the South Koreans and the Chinese and the UAE and Australians, all of them involved in one way or another to use their expertise to see how can they get involved in the various aspects of identifying, extracting, and utilizing resources. So we have gone from 2 countries in the 1960s trying to race for the moon, and now we have different countries and companies all in this next space race for the moon. It is not just the large aerospace companies or the big government, it's small companies that are now injecting themselves in what we call the space resources value chain. These are startup companies, medium-sized companies, companies that have operated only terrestrial, never in space, but now they're saying, I'm going to be the one prospecting. I can be doing the drills. I can do the extraction. I can do all the infrastructure. We're going to need power, communications, transport. And I can fill probably 4 of these different slides with the amount of companies that are now involved. And a lot of these companies are here in Colorado. Yes.
Where's your space?
I should have known that you were coming. That's why I said that I can fill 4 of this slide, and Sierra Space will be in the next one. All right, okay. So now you're seeing that the interest is from space agencies, for countries, from small companies, launch companies. So even at some point, there was so much interest that there needed to be some education about this, the realities of this, and not just the hype and all the material and all of the different news that are going around. So even academically, Colorado is playing an important role. The School of Mines launched 7 years ago, the first program in the world educating not just scientists and engineers, but economists, entrepreneurs, and policymakers on the field of space resources. And given the interest around the world, we started offering certificates, masters, and PhDs, all of them online, because these are people coming from all sorts of companies. They cannot move to Colorado, and we had to reach everywhere around the world. To the point that right now, we have about 148 students from 5 continents, 24 countries, from all professions. You got scientists, engineers, economists, we even have lawyers too. And from all sorts of fields, because the interest is, how can I be the person in my company that can know about this, or I can form my own company, or I can participate on it. So great. The interest is from governments, from companies, from education. Now you may be asking at this point, this is great, but is this legal? Can I just set up operations on the moon and asteroids, extract the materials, sell it, make a profit? Aren't there some treaties there telling us how to behave? You know, the Outer Space Treaty of 1967, signed by more than 117 countries, that very specifically said on Article 1, the exploration and use of space shall be the common province of all mankind. Article 2 talks about prohibiting claims of national sovereignty. A country cannot own the moon or cannot own an asteroid. Or the Moon Treaty of 1979, in which just 19 countries signed it, because by then they say, well, maybe there's something else. And so we gotta be careful. And not just, is it legal? Is it fair? Is it just a matter of the superpowers doing this and taking advantage? Or is the whole world, as it says on Article 1, can enjoy these resources? This is a very important question. And so things started moving very rapidly in terms of trying to not bypass the international treaties, but try to see if we can do these resources. And the United States started with this in 2015, with the U.S. Commercial Space Launch Competitive Acts 2015, signed by Congress, by Senate, by the President, in which says very clearly that if you're a United States citizen or a company, you are entitled to a resource and you can possess it, own it, transport it, use it, and sell it, according to the international obligation. As soon as the United States did that, Luxembourg the following year became the first European nation to offer a legal framework for space resource utilization. followed by the United Arab Emirates, and then by the Japanese in 2021. So these are countries trying to make laws on their own to try to attract individuals and companies to work from their countries. But this is just a few countries. And so there have been efforts to do this in a more global way. In 2016, the Hague in the Netherlands, the Hague Space Resources Group, brought 35 countries, developing countries, underdeveloped countries, that started saying, well, how is that can everybody play on this and enjoy the resources? Their work was done by 2019. That has gone to the United Nations. Then it has gone to the Office of Outer Affairs. There's now a subcommittee in the United Nations on space resources that by 2027 is going to come up with its legal framework. But still, some people think, or some countries think, that this may take a long time. Everything that goes to the United Nations may take time. So they tried not to bypass, but to form clubs. The United States started in 2020 forming the Artemis Accords, and 9 countries signed an agreement of how we should behave if we are in the moon. We have to regulate the launches, who's going to extract, where you're going to do it. And this has grown tremendously. Almost every month there's a new one. Right now we have about 53 countries. There's on the way, it's 53 countries that have signed on to the Artemis Accords. But at the same time, got China and Russia doing their own club, the International Lunar Research Station. And now they have up to 13 countries saying, if you come to the moon and we play by our rules, then you're part of the club. So now you have 2 poles. You're seeing the same reflection of what's happening on Earth in space. And we're going to have to be careful, because we better communicate. This is very challenging if we don't have to avoid any conflict that may happen in space. So with that, what I have tried to do is give you an idea of how space resources have a promise, both for a large amount of scientific discoveries in the future, because we're going to be able to travel further, to have larger payload. We're going to finally be able to inhabit on the moon or Mars. We can lower transportation costs. We can refuel in space. But at the same time, not just scientific exploration, but how is it we can increase the number of commercial activities and truly start incorporating space into our global economy. It will be up to all of us on Earth to learn of what we've done here on Earth, how we have benefited from resources for thousands of years, and try to do the same thing when we go to space, but also learn from all the bad things that we have done in the process of extracting resources, as you know. So hopefully we can do it in space in an efficient, in an economic way, but also in a fair, in a responsible, in a sustainable way, so that we can enjoy both the benefits of space resources for science and for applications, and that we can fulfill the dreams of those that came before us, that were able to foresee the value of space resources. Like a good friend, Konstantin Tsiolkovsky, that was able to see in that beautiful, elegant rocket equation the value of space resources, and was able to put those ideas and those thinkings into poetic terms, because he was also a dreamer. When he said, "The Earth is the cradle of humanity, but humankind cannot stay in the cradle forever." Just like humans escaped the cradle in South-Southern Africa, use their resources to explore every corner of our planet, let's hope that space resources can do the same as we venture into space. And with that, I'm open for questions.
Questions, people? Pardon me while I put my brain back together. I blown
Over
away.
there, I'm back. Yes, you are the one.
Okay. So as you said, there is some, Marshall, that's not the word, well, moon sand on there. However, moon
Regolith.
sand, what? Regolith. Right.
Regular.
However, regolith appears to be incredibly sharp. When plants grow in terrestrial dirt, they're able to grow. However, one concern could be that regolith would be too sharp for the plants and would cause damage to the sap.
Yes. There's already companies trying to treat the regolith and pass it through a grinder, like a ball mill, to round out the material, because exactly that point.
Wow.
Because you're gonna need that. Not only is sharp, is electrostatically charged.
Yes.
And it's very fine, and it links to everything, and so you're gonna have to prepare that material for whatever it comes next. Is that for extracting something or for growing plants? Absolutely. In fact, Brazil is actually interested now on lunar agriculture and how to do that. So they're finding that as a problem. And right now, what we do is simulants. At the School of Mines, we actually make simulants, but no simulant can replicate what lunar regolith is going to be. It's very difficult. And hopefully, with the visions that we have, we now get the chance to get some of the properties of this material. So good point. You had about.
What is Caterpillar making to go to space? Seriously?
Caterpillar wants to become the company to be able to excavate and do things. In fact, the Racer rover that I mentioned to you, Caterpillar is working closely with NASA. In fact, there's a competition that takes place every year where it's sponsored by Caterpillar. And they're doing it for two reasons. Yeah, they want to be the first, but they're seeing if you can develop technology on Earth and on space that we can use here on Earth, like full automation, we'll take it. That's the bottom line now. In fact, many mining companies, if you talk to them, they're saying
It's a two-way thing. Yeah.
yeah, they're saying, well, it'll be space is great, but give me technology to operate in very extreme environments, radioactive mines, very deep, robotically, use waterless extraction processes, like because in the moon you don't have water, you can extract without water. That's where they're interested. And they're saying in the mining world, there's these junior companies, they call it. Let the juniors go and they do something, we'll buy them and then we'll get into the moon. But that's the thinking. But they're very interested on this. I mean, in fact, you will see what is Rolls-Royce doing. They're developing nuclear power, all the infrastructure. So these big companies are seeing potential opportunities. They're cautious, but they're thinking about it. Go ahead, Bob.
Oh, thanks. Yeah, great talk. My question is about this sort of near-term so-called lunar economy, because I get it in the long run, we could use all this for bases on the moon and the next step of humanity. But in the near term, NASA's been selling the commercial lunar payload services as a public-private partnership in which the first missions, like Blue Ghost, didn't have any commercial payloads on it. I think, they've had a couple of commercials, even the iSpace's lander has some little, paid rovers on it. And so they're trying to develop this, having the companies start an economy. And, other than, when are people gonna get tired of sending grandpa's ashes to the moon if that's even ethical?
Yes.
It's like, what's the real economy for these companies to make money on the moon?
It is like everything that happened for railroads and airplanes and biotechnology and lasers. The government definitely will be the first customer. NASA is looking at it from the point of view, if commercial company not only can take me to the moon and take your payload to the moon, but if they can extract the oxygen that I need to have a base, if they can extract the water and they can do it cheaper than I can, I'll take it. But they're very cautious too, because they don't want to put it on the critical path. They don't want to send humans there and say, there's oxygen to breathe. Is that a good oxygen or is that good water? So they're cautious now, but they're letting companies say, okay, you go, try it. If you can prove to me that you can build a habitat for me, that you can do that, we'll take it. It's low cost and low risk. So those are the first customers. That's the first. It's not an economy because it's the government, but once that happens, who knows what's going to happen after that? Maybe that's why right now the most short term is refueling in space. That's going to be important, like orbit fab or recycling space debris. The moon will be next, but mostly for space agencies. Eventually, once you have a settlement and the like, maybe you start doing this, but you're right. It's going to be.
So if I just restated that, you're saying that it's not that they're creating their own economy and making money just on their landers. It's that they are wanting to demonstrate technologies they can sell forward still downstream.
Correct.
Okay.
Yeah.
Thank you.
I mean, you were in a mission that proved that with a low budget, you can actually get to the moon. NASA said, I will take that. Now, can you give me oxygen? I'll give you oxygen. Can you build it for me? I'll take it. And now it comes to the companies to prove that they can do this reliable and not crash all the time. It's that's difficult. That's difficult. Yeah.
Huge risk.
Yes.
My question is, this seems like probably make the first step
thousands of years ago, but this seems like step number 2, number 3. The Earth is limited in its lifespan. Eventually the sun, I mean, we're talking 4, 5, 6, 10 billion years out. So long term, eventually we have to leave the planet. Hopefully take some life forms, have a chain of solar systems to get to a habitable planet. This would be, you know, millions of years down the road, but is there anybody kind of exploring? I mean, that's seems to be inevitable, but it's so far away, but we are obviously taking the first steps.
That's the ultimate goal. So people that look long-term is saying, this is how it's gonna start, and maybe NASA will benefit and maybe some things, but in the end, if we start now having a base in them, and we can start having some work there, some quantum computing centers or whatever, and then you start expanding it to Mars. Eventually, I don't know, I mean, for me, it's really hard to see beyond 10, 15 years. People actually start seeing, well, if you can have all the extraction done in space and not on Earth, and then at some point move out, that's the ultimate goal. For me, it's difficult to see that because this term of being multi-planetary species is just, I mean, we may be able to go to Mars, maybe, I don't know what it's, probably that's the only planet, but eventually, you're right, the sun is gonna catch up with us. I don't know if we can go to exoplanets, and I cannot foresee the future, but that'll be the ultimate thing, you know, how can you make the human race is gonna morph into something else because it's gonna have to live in different gravities, but that's far out. I mean,
And it could take thousands of generations just to travel across the galaxy hopping.
and how many of us,
generations and generations.
how many of us will be able
How can
to?
we get nuclear propulsion?
That's
Gotta go fast, yeah.
so now you got people working on nuclear propulsion. How can you go faster? So you never know when some technology is going to develop that is going to change the way that you look at the future. And so we're just working on it and hoping something's going to happen.
The other side is how long do we live? We live for 80 years. What if we live for 800, 8,000?
Yes,
Now, you're off of Centauri, there's a couple centuries, no big deal.
genetics
Just freeze and wake up and there you are.
genetic technology may change the way we adapt to other places. These companies that are doing 3D printed organs for Pete's sake. And so who knows where this is going to go? I mean, it's really hard for me to see that far away. Yes.
Bringing back to his slides earlier, when we moved out of Africa, we were thinking about food and how to move things across land. Nobody in that time could have imagined aircraft that could have taken those resources from another continent they didn't even know existed and brought it to them at a moment's notice.
Absolutely.
By the time we get there, there will be technologies we can't even hope to fathom.
And that's 100,000 years. Things are moving so fast now that it's almost exponential the way that we're, I mean, in my lifetime, I have seen so much that I cannot predict anything. I cannot say no anymore. I mean, these are things that are happening very fast, but you got a point. Yes.
What about AI, artificial intelligence? And I wondered if some of your students are working on that or.
Other than cheating on exams. Yeah, AI, I think it has a room. It's developing, that's one of the things that is developing so rapidly that I don't know how AI may be able to make decisions on robots that aren't somewhere else without us having to send signals and all that. They may be able to do things that we don't. These things is moving so fast. You're right. That may be machine learning and all that. All these robotic technologies that are being developed now are incorporating this. So you don't have to depend on signals that take 20 minutes or so to get there. Do things.
They hallucinate.
Yeah.
I can use it.
Yes.
I was always gonna say the same thing as
Can't trust it.
he said. That the next big thing that's gonna change what happens is mode of transportation. And, you know, if we can, you know, play a little game, if space travel is and has already happened and we find out that, you know, this actually has existed, we'll find out that, you know, that this thing of unidentified flying objects has some reality and we get the new mode of transportation, that'll that'll change the game.
Transportation is big. I mean, to go to Mars right now, people that want to go to Mars. And it takes 2 to 3 years just to go there, live, come back. If you can speed it up with nuclear propulsion, boy, things can change radically. So, yes.
I was wondering a couple of things. Back in 2006, I participated in a Department of Energy study to beam power from the rim of Shackleton crater. They had like a 10 megawatt solar power.
Yes.
And they had to beam it 10 miles to 5 different mining stations that were mobile. We looked at that versus running wires down. It was a trade study. The things we found out, you know, that the dirt is electrical. It float.
Yeah. That's right.
You know, and the temperatures that they have to deal with in the bottom of these craters are something that we really don't have a whole lot of experience with in making parts and making machines that will survive down in those temperatures.
Yeah.
Can you comment on both the power beaming and the temperature thing, and where are we at with trying to develop things for that? I know we have the rectenna.
Yes.
To get power off, we were about 50% efficient. But can you comment?
This is
Dr.
interesting.
Zoya Popovich is in CU. She was doing the rectenna stuff and
Yeah.
everything that helped. Yeah.
This is interesting that you were talking about this study from 2006. Just 2 years ago, we did a study from School of Mines and Lockheed Martin on power beaming. And we resurrected your ideas actually, but now with newer technology, and we were able to, and we have this, we call it dirty vacuum chambers at School of Mines. We can put regolith and all that. But we had we put a battery and a transmission and all that inside this chamber. And we simulated ultra high vacuum. Plus, we have a cryo shield that we can bring it down to liquid nitrogen temperatures minus 190. And first of all, we found issues with vacuum, it's shorting and all sorts of things, but we were able to solve that. Temperature is an issue, but we were able to actually win one of the competitions on beaming power. And then at Lockheed, we did it. It was like 3 kilometers from one place to another, obviously in atmosphere, but the same technology. But we're trying to do it at the right conditions.
Right.
Vacuum,
Yeah.
temperature, radiation, and all that. It's challenging, but I think that's the way to beam things down. You don't want to just have cables going down. So thank you for that.
So it's still going on.
It's still going on.
Programs that are
It's still going on with better
We're
technology.
still doing this stuff. We were
Yeah.
just kind of the first ones to start looking
Yeah.
into it, I think.
Yeah.
Yeah.
Absolutely.
Dr. Abbud-Madrid,
Yes.
I'm in a Zoom call with you.
Yes.
I have a question. By far, this is the best presentation I've heard in the period of time I've listened to SkyWatchers. So thank you very much.
I'll tell my students.
But what I see from your presentation is that the real value is in the exploration of all these minerals and metals, and that we're going to learn technology that can be used here on Earth. I mean, there's so much that we don't even know about our oceans that will probably, the technology will probably be used for some of that, or to go into areas of the world that are somewhat uninhabitable on Earth that we can use for the same purposes that are being used out in outer space. So, I mean, the value is in the knowledge and the technology that comes out of it. I mean, even 50 years ago or 40 years ago, satellite technology, people didn't even imagine that we could communicate the way we do. But that's due to space research.
You're absolutely right. And in fact, that's why I mentioned that companies here are seeing how they can bring that technology here to Earth, because robotics is advancing very quickly, and you need robotics in space, and they're quite advanced. If you can use it here, just imagine going to the depth that you have to go now for mining certain elements, for radioactive material. If you can use that technology, that's the interest. And you mentioned something interesting, science and technology. So science right now, for example, is very interested on the moon to be able to catch it before all this activity happens. You know, scientists are concerned, and maybe Bob Green can tell us about it, that once people start doing all these things, you're going to contaminate things. But science can inform technology, and technology can also inform science. If you have one of these drills and you can identify the elements that you find, for scientists, that will be extremely valuable, and also for technology. We just need to get along between the two communities. But you're right, developing technologies that can be used for us, the billions of people here on Earth, is probably one of the most important things that we can get from space, as we have learned through the 60 years that we have been doing this.
Well, and there's two other factors that that were raised in my mind as you were talking. Historically, it's when businesses get involved in the technology or in the research and science that things progress very quickly. It was, in the agricultural revolution, the industrial revolution, the communications revolution, the internet revolution. I mean, that they're all moved so quickly because of businesses getting involved. And honestly, I think one of your best slides was the number of businesses that are interested in doing work in the field of space research and resources. I was just amazed at how many companies were interested. And not only here in the United States, but also in other parts of Earth. So that was one big factor. The other, which was very interesting to me, is that there was no mention whatsoever of microbes and potential disasters. And I remember I was in the space field in 1976 and the Challenger 86 and the Challenger accident, and all of a sudden everything died in the field I was working in space. I mean, NASA didn't do anything for so many years, and so I see potential issues in some of this research, because most of it will not be used here on Earth for some time. It'll take time to develop some of these technologies. But because business is involved, I know it'll progress a lot faster than we even dreamed. And someone mentioned AI, you mentioned 3D printing, but there's also 4D printing and 5D printing now, which I'm sure can be used in space.
Yeah, I think you bring up two important points. How fast this has moved. Like I mentioned, 10 years ago, NASA was thinking this on the far future. Then companies got involved, and this thing went just so fast. I remember the first meeting that we had with Lunar Outpost. Lunar Outpost is a company that is here in Colorado. They came to us saying, we want to put a rover on the moon. We thought they were crazy. I mean, you want to do that? Why? Well, we just want to prove that a company can do it. And we're on the moon just 2 weeks ago. They couldn't get the rover out, but they were communicating. And you got intuitive machines and Firefly and all of the honeybee robotics in just a matter of 7 years or so. So that pushes even technology much faster. And just like you said, this is going to go exponential. Now, you mentioned the other side, microorganisms and all that. That's a concern for Mars, for sure. I mean, we're going to start extracting things from Mars. We got to make sure that we don't bump into bugs and microorganisms there, and there's planetary protection and all of that. The moon is different, but still, there was some complaints about an Israeli payload that carries some bugs that they didn't tell anybody, and that's a concern. And then Bob brought something very important, the ethical issues of space. I've been giving talks on this for I don't know how many years. At first, people were enamored with the technology. Then the question started being about the environment. Well, are we going to struggle the water there? And who's, are we going to leave no water on the moon? What's the deal? And then the ethical questions started coming. With this issue of bringing ashes to a year ago or so, indigenous people in Australia and here in the United States started complaining. Said, look, the moon is an object of adoration for every culture since the beginning of time. And for some of them, this is where the ancestors go and live. Why are you contaminating it that way? So these are very important issues that have to be addressed. So not just scientists and technology have to get along, but also cultures that we have not taken into account. The perfect example of how to do it right is Mauna Kea in Hawaii. When you have a place where they consider sacred by the locals, but also a great place for telescopes. And they have somehow figured out how to coexist. And these are the issues that we're gonna have to deal with, not just microorganisms, but different cultures and asteroids, nobody cares, nobody sees them, but the moon is something that when you start seeing some changes on the moon because there's some activity, there's gonna be some complaints. So just something to tell you what's going on here, but there's.
But how do we know that there are not microbes in those deep into those craters that you were talking about in this on the South Pole? I mean, we have life on Earth that doesn't come to life until it's spring. You know, we have animals that burrow into the ground and literally don't come alive until there's a little bit of water or heat involved.
That's a good point. I was actually part of the Planetary Protection Committee of the National Academies of Sciences, and we did a study for the moon, and the conclusion was there is no life on the moon. There may be prebiotic material that came from asteroids that is stored down on the permanently shallow regions, but at those temperatures, at that radiation and those environments, life is just not possible. So,
but that's life as we know it.
As we, yes, so it's good to study that material that could have come and in the right conditions may do that, but the moon right now it's categorized so that you have to protect those things for science, but not necessarily for life. Mars is a whole different world that definitely could have life.
Well, Musk wants to bypass the moon and go directly to Mars.
Yes, so that's going to be an issue.
And he seems to have a lot to say these days.
Yeah, but to make it happen, it's going to take more than 4 years. So who knows?
That's true.
All right, I think we need to wrap it up here. We got a couple other things to go. Let's thank our speaker here. That was great. We need to kind of strike the set and get things reset up again. So it seems to me it should take 5 minutes. Probably means it'll take 10. But meanwhile, discuss.
How about yourself? Hey,
Yeah, Leonard's gonna give his talk.
Actually,
Yeah, okay.
He says that just keep adding to it.
Connected computer, I just connected
Okay.
this
is your adapter, right?
my adapter. You got all those things in there. Let me get all my stuff here.
No gimbal.
Take a peek at the meteorite.
Sure.
My sister has a rock and she's like, I saw this meteorite.
Yeah.
This is to pick up the rubber ball and said that didn't make it.
Just get stuff out of the way.
I'll do that. Connecting.
Cheers. One less obstacle.
Then,
Yeah, we're not putting stuff away yet.
I was just gonna move that chair out.
Oh, no, I see what you
Run
mean.
back.
Yeah.
Connection.
Plug it in there instead.
There you go.
Terrific.
They're confused. My computer. Throw that out. Technology.
Oh, there you, that's why.
Very knowledgeable person there.
Leonard said we could cite this.
Oh, really?
I can see it. Quick audio check. John Williams, can you tell me if you guys can hear me?
Can now, you were muted a minute ago. It's good now.
Yeah, I just noticed the mute on the thing. So you can hear us fine. So Leonard, who has been having some allergy voice issues, is going to get his talk, but he's having trouble talking.
Hey, you're cruel, Dewey. Right. Yeah. We can open a love talk for
Yeah, well, since I don't know what to say, it would be, and here's another slide, and here's another one.
You can't because the slides are so minimal. So you don't-
Yeah,
throw that in the
yeah, I
slide.
know, it's all in his brain. Oh, wait, one more thing. Scoot back, back some of this back. Because, okay, I have moved this forward. Okay, yeah, one last light thing.
That's smart. I already find out what it's.
Yeah.
Hey.
Whoa, okay.
George.
What? All right,
Talk, right?
I'm ready. All right, I hereby turn it over to Leonard. Okay, we got this thing. Should be working.
Ready?
Yep, you're on. Here's Leonard. Go.
Wait. Okay, this is not working. Here we go. Am I correct?
Go, let's see.
Right.
Right. Go forward. Back. I do have to shake it loose and I do, so.
Oh, so I
I'm good. There he goes. Next. Hey, I'm on a near-death experience here with my voice. Barb and I have a tendency to leave our Christmas tree until March. And I took the thing down and I got so much pollen coming out of that thing. I'm hallucinating now, but it's pretty standard operating procedure here. But what a week, the last couple of weeks. Landings on the moon, crashes on the moon, Starship blew up. It's on and on. I mean, I wish I was 13 again and have a better voice. But there is so much happening at once, and it's a really impressive time with failure and success. And I'm gonna skip this because Bob's gonna do a little update on, it really is something to know somebody that landed something on the moon. And it worked.
Do the landing.
Yeah, well, I know, but I'm telling you, to me, it's a great thing, and getting on the moon is a big deal. So Blue Ghost Mission 1, Firefly Aerospace, mid-January, landed on the moon on March 2nd. Now, the bad news, kind of a competitor in a weird way, is Intuitive Machines. Another company tried this, and it was a replay of their failure that they did in February of last year. The thing tried to land, skidded across the surface, busted a leg, looked like it broke a leg, wound up in a crater, died in a day or so. I'm not a big fan of these people. They don't tell you everything that happened, but anyway, one casualty in this last couple of weeks, it looks like we lost the Lunar Trailblazer, which was a lunar orbiter built by Caltech and Lockheed Martin, and as far as I could tell this morning, it was still lost in space, and I'm not sure that mission is going to be retrievable, but was really important because it was going to be a lunar orbiter to look for what Angel was talking about, the water ice on the moon. I mean, it was a fairly significant contribution to the search for water ice on the moon. So may have lost that. So we had, great success with Firefly. IM2 Intuitive Machines crashed. Lunar Trailblazer was lost. But the point is we're really trying to get this down. And getting back to the moon is going to be a long-term event, even though I lived through a lot of these landers way back in my youth, but it's exciting, to see the private companies attempt all these things, and I must say, Angel's talk is just outstanding. I mean, that's why I go to the School of Mines every year. That place has got more stuff going than any other conference. It brings the best of the world together in a meeting at the School of Mines, local, about where we're going elsewhere. And that's a terrific talk. And I got to remember we got 10 humans in space right now. Right now on the International Space Station, it's flying by as we talk. Almost 10 people up there. They're all squeezed together. These folks just arrived not too long ago. And we also, you gotta count in the Chinese. They got their own space station. Don't forget them. This is the big news. You know, they just had a spacewalk yesterday or 2 days ago. And that's the third spacewalk on that space station. They're making a lot of progress. I always keep an eye on China. It's going to be the wild card of it all. And guess what? The stranded crew is back. These poor people had to go into space. They rode, you know, the Boeing built Starliner capsule. They got up there. The mission was kind of fouled up early in the rendezvous with the space station. There were a lot of problems. And so, you know, despite it all, they weathered the storm of criticism, and, you know, they're stranded. They're going to be never come back. And she's losing weight, you know. But Sonny Williams and Butch Wilmore, they went up on a Boeing Starliner capsule. A lot of propulsion issues and to get there. And they had to bring that capsule, Starliner capsule, back uncrewed. So they were, you know, quote unquote, stranded. But they were reassigned to SpaceX Crew Dragon. This is, you know, the thing that just happened just a couple days ago. They got back down on the ground. They're doing fine. You know, the thing about this mission was really a subliminal message. It was NASA really moving up the gauntlet about safety of crew. And I'll give credit to them because they got a ways to go on some other issues that they're dealing with now. But, you know, holding on to those two crew people and bringing them down on the Dragon capsule proved successful, and it showed kind of a robustness in our ability to not put humans in danger in low Earth orbit. However, man, if you want to have a heyday on the internet, it's like listening to the space cadets. And I listen to them a lot. I mean, I'm on everything. And I don't know where we're going. But the cutbacks, you know, Elon Musk is a hate-love guy. Donald Trump's trying to cut back on federal resources and skew things. But all of a sudden you start seeing Boeing, you know, we need the SLS, the Space Launch System, you know, write your Congress people. So you know it's trouble. And so something's coming. And how this is going to sort itself out, I mean, I've heard everything. I mean, I've tried to write about it, but I'm on the low end of understanding what really is going to happen. Not tomorrow, but like an hour from now. There are things happening pretty much real time. And it's very hard to see how NASA avoids this kind of circular motion that's going on now. And I don't know what it means, you know, for NASA cutbacks. You shut off Voyager, you kill. I've heard everything, you know, people are panicked. People are losing jobs. NASA's restructuring. And we got a weird thing going on. And I'm really mad about this. You got a guy that Trump asked to be the NASA administrator, and he's flown in space, and he's a no-show. Because he's a no-show because we haven't had a confirmation here. At a time when NASA needs guidance, this guy's is a no-show. And we need to get going on this and get him in there. And God help him, because it is way beyond his skill set. So I don't know where we're going, but from a writer's standpoint, we got some real problems coming here about the future of NASA. What's gonna get cut, Artemis program rearranged. Oh, forget the moon, let's go to Mars. I don't know, but you know, that's why I love writing. It's so much fun. I think that's enough for me. Let's, Bob Grimm, come on, give me that.
You have the video?
We have the video. Let's go.
Can I control the video?
Is that what's on the thumb drive that I got from,
I don't know.
where's the video?
That's the video. John had it.
I
John
have it,
has,
but
it's ready.
won't be able to control it.
Well, I just want you to like, it's only like 4 images. I just want to like be able to speak to each one briefly before we like look at it.
And then I
Yeah.
also have a couple images that John Asseloff gave me.
Yeah, because I asked him to take pictures.
Okay, so what order do you wish to do that? The video before the
Let's
pictures?
do
or
the video
pictures
because the pictures are of the right before sunset at the landing site.
Okay.
So- Okay, so
first?
yeah,
Well, after Bob's done, then Clark and Y have some stuff to show about auroras and their little trip. And that will be the end of our show.
We need picture.
Yeah,
so
they got some neat
you're seeing
pictures to
this on
show.
your screens, but not this screen.
So
So,
it's not showing on the main screen?
yeah, I just need to get it up on the TV screen. So
Okay.
Okay,
that's your
so-
video right there.
I'll just, okay,
Let me
you can, yeah, just leave that for now, just go full screen.
know what I need to do is.
Okay,
kill
so,
this PowerPoint.
Blue Ghost landed successfully, first United States landing this century. This is the commercial service, so NASA selected 10 payloads. In 2019, we were selected, and 7 of them were competed externally. That was with the lot we were in, and 3 of them were assigned by NASA. So we're doing this thing called lunar magnetotelluric sounder. Magnetotelluric means magnetic and electric. We're measuring electric and magnetic fields at the surface of the moon. And so this is the rendering of the lander. And this thing that goes up vertically is a mast. It carries the magnetometer on it so that it's away from the lander to have less interference. And then there's 4 spring launched electrodes that came out of the side of the lander. And those are the measure the electric field. It's like a voltmeter. So let's just roll it, and because I pretty much explained it all.
How excited were you though about getting this thing? You worked on this for how long?
Since 2019.
Okay,
So that's what, yeah, these are all around the sides of the lander. This is the coolest thing for us. We saw this at like 3 a.m. And then this is the deployment of the magnetometer. So can we just go back? Okay, this is what we're doing. All right, that's the whole thing.
no,
I just wanted to see that, I mean, watching that thing launch, so that it is a spring that shoots it out like 60 feet. And yeah, so we're in the middle of the night when our window came up to do this. And they said, yeah, we could see from the data that they had deployed, but then Firefly downloaded the video and we pulled it into our little op center in Boulder and saw this and about hit the floor because yeah, we didn't expect to see video. I mean, originally we're just gonna like look at our data and have them take pictures of it later. And they said, we want to take video. So we said, great. And it turned out to be like, looks pretty cool. Yeah, so I mean, that thing is straight up. It's a lens distortion. So we're gonna rectify everything, and you can actually see the electrodes lying on the surface in pictures from later in the day. It was 2 weeks, working all hours. It's supposed to be just turn it on, let it take data, and that's it. But there was a lot of activity going on that we had to adapt. A lot of things happening during the mission. In the end, NASA was able, and Firefly were able to give us much more data volume than we expected to get. And then a long duration, a continuous duration near the end. That we really wanted to have a long continuous measurement sequence, and that came together, in the last 4 days. Yeah, and then we sat around there was just two of us left, everybody went home. All of our other operators, there was two of us left, me and the project engineer. So yeah, we just sat around on Sunday afternoon and drank beer, waited for the sun to go down, which it did, and we could see, we turned our instrument off a little earlier. We didn't think we were getting very good data anymore, so we turned off a little early and gave some energy, back to the lander, and they just rode into the sunset. And that was it. Now
Yeah, now it's dead, right? I
now
mean,
it's dead. Now, they did do some things that we could tell from the sequences.
Yeah.
The procedures that they're making it so it could be favorable conditions for it to wake up again. It's not designed to wake up again, it did its job, but it's not out of the question that it could wake up.
we got a 14-day
Yeah. it's
night
yeah.
day cycle,
Yeah,
so.
we gotta wait till the next crescent moon. Will be.
And his experiment was one of what, I guess, 10,
Yeah.
and, as
Which
far
reminds
as,
me, I need to talk to Ango about, did you see Lister? Did you see the drilling?
Yes, he was fantastic.
It's really weird. I mean,
yeah,
it blew out big chunks instead of nice,
Sparks were coming.
Yeah, it wasn't like a bunch of 70 micron particles.
No.
Something weird is happening. So,
Yours was a seismic?
no, it's electromagnetic.
Oh, electromagnetic.
So it's measuring natural electromagnetic fields, very long periods of minutes, hours, even days, and those long periods penetrate very deeply into the moon, many hundreds of kilometers. So we're trying to understand the internal temperature of the moon and its evolution.
Bob, if Firefly comes alive, can you turn it on?
I mean, NASA's never said anything, like NASA bought what they bought. And I think all the instruments have gotten, really, really cold. Frankly, I would say we don't need to. I mean, it's gonna be more of the same at this point. We need to understand this data. And actually, we have another entire instrument going in 2027. Same thing is gonna go to Schrodinger crater on the far side and that is with a thermometer and with a heat flow again. And so we're gonna do it better somewhere else. So I want to analyze this when I'm done with it, and then look forward to the next one.
that's Lugos 3.
That's on Ice-Base Draper.
Draper.
Two pictures.
Yes, okay, so then, well, I'll let John describe what he did, but I put out an APB like, this is sunset, this is the Blue Ghost moon, this is their moon.
Hold on one second. John Williams, you need to stop sharing so that we can share
And then we need you.
these pictures.
I
I will share.
Let me just point out where the landing site is, and then John can describe the pictures. It's right on the far side of Mark Christian here, so, we're hours away from sunset.
Okay,
there. So,
John,
please.
well, John Williams is still sharing his screen,
Oh,
so the
okay.
Zoomers aren't seeing
can-
any of that.
Okay,
You can take over.
I can send a request.
well, okay, so before you describe what you did, I'll just say thank you, and then, because I wanted a shot of the moon, to remember the mission by, and this is, to be part of our archive, so thank you.
You're welcome. I was happy to help, because I knew it was a big
There you
deal.
go.
Well,
Thank you,
Bob asked me,
thank you, John.
I wrote out an email saying that Bob wanted some pictures. And we had this lovely cloudy lunar eclipse. And my gear was sitting right near the door because I had it all out a few nights before. So I thought, it's just gonna stay there and we'll cross our fingers. So yeah, it was clear, but it was very turbulent and windy. And it looked sharp there, but it could have done better with a steady night. So I took I shot basically over 2 separate periods, one around 1 AM and one around 5 AM. And you can see that the terminator is moving over Mare Crisium compared to the first shot in the second shot. So,
You want the second shot now?
yeah, sure.
There's the second shot. See the Terminator, it moved.
So I think
the sun set on the spacecraft somewhere in the afternoon.
It was, yeah, it was
Little
some hours
later?
later. Yeah, it was
Yeah.
like, 3 o'clock in the afternoon for us,
Okay,
I think.
so.
It might
that's-
help to point out that Mare Crisium is that mare that's in the, right there.
Yes, thank you. So, yeah,
That's all.
You know,
yep.
thank you, that's, all right. So. John Williams, you have, the stuff for, Clark and Rye?
Yep.
Okay, I will stop sharing then and let you do that.
And then we need Clark and Rice this week.
Okay, and now, Clark Chapman and Rye. We should put it up here.
Okay, well, we planned last spring actually to go to Norway near Solar Max above the Arctic Circle in the hopes of seeing Aurora Borealis. So in fact, we and a couple of friends of ours who tried to see the aurora a few years ago, but the airplanes screwed them up. The four of us went to Alta, Norway, and arrived at a resort on February 28th. And while we were having our first dinner at this resort way up above the Arctic Circle, they suddenly came in and said, "Hey, come out and see the aurora." The previous picture showed the aurora kind of during dusk. The bright spot there is Venus. And Y took these pictures with her iPhone. I had my old 35 millimeter camera, and the aurora was spectacular enough that I actually saw a bit of the aurora in my pictures, but nothing beats aurora photography like modern smartphone.
Right.
Why do you want to talk about it?
I would just like to say one thing that's really impressed me the most, and that was the speed of the constant changing of the visuals. It was like nothing I could ever even imagine. It was just constant, newly creative visuals that was just mind-boggling. That's all I have to say about the Aurora Borealis. It was beyond spectacular.
Yeah, well, we then went back in to eat some more dinner, and about an hour later, they said, "Hey, you got to come out now." And this picture is the first of a few taken later in the evening of the 28th of February. And the locals there said it was the most spectacular aurora they had had in over a year. So we really lucked out.
Yeah, we certainly did.
Hey, you can cycle through these.
Wow.
It was just amazing. I once saw an aurora when I was a teenager back in Buffalo, New York, and this aurora exceeded that. This was an incredible experience for everybody there. And then we actually had signed up for an aurora hunt, and it took place on March 2nd in the evening, and we went out and sat for 3.5 hours out by a campfire or warming up in a minibus. Okay, and right here, now this stop here for a moment. So we sat there and the sky was totally clear, brilliant stars, the crescent moon had long since set. And, there's no cities around Alta, Norway. And so we got on the minibus and we're headed back to the resort. And 5 minutes from the resort, the driver suddenly pulled over to the side and said, "I see lights." And so we got out, and the last several pictures here are the aurora that we saw at that time. And I don't know.
Yeah, the reds showed up here more than before, and it's just amazing.
And right down here near the bottom, just above the trees, are the Pleiades. You might see them just at the tip of a tree in the center of the picture. It was, I mean, if we hadn't seen the big aurora 2 nights earlier, we would have been satisfied going to Norway just to see this aurora. But anyway, it rather quickly faded away again. And anyway, we had a wonderful time in Norway, and we were rewarded with these two auroral shows. Oh, well, yeah, at this resort, there's an ice hotel. I mean, we stayed in a lodge except for the final night when we actually slept for about 4 hours in the ice hotel. But the ice hotel, which they make every year, they do ice sculpting, and this is a Medusa. That's why and myself in front of this ice Medusa. We're there for scale. And I think there's one more picture, maybe. I don't know. Is there one more picture?
That was all I had, sorry.
Oh, okay. Well, okay. Sisyphus will have to be seen later or another time or not at all. But anyway, certainly, I think we were thrilled with our whole trip to Norway. It's a wonderful country. They're a little aghast about what's happening over here, but Norway was working fine, and the skies cleared and the sun did its thing.
Yeah.
Is it freezing?
Our audio hung up for a second there.
It was at the
Yeah, we did on Zoom too. There is a chance tonight of aurora in Colorado. The sun threw something at the earth, and so if it's clear to the north, go outside and check it out.
Well, it was about a year ago that there was an aurora in Colorado, and that's when Y first tried out her iPhone on the aurora and got, pretty nice picture of red glows from here near Netherlands.
Yep. A friend of mine got a picture of aurora near Cortez, so northern Colorado should be good too.
Yeah. Well, cool. Thanks, guys.
Yeah.
You want to be done?
Yeah, done.
That's it for us.
Okay.
I'm asking, do you want to see the other images we had, or call it a wrap?
Oh, you got some images?
Oh,
Yeah, from Dave Elmore and myself, but we can show them next time.
No, show them.
You want them now, folks?
No, we're here.
Yeah, we're here.
Yeah. The vote here is show them now.
All right, so me first. I was part of the live stream for time and date again with the lunar eclipse. It was cloudy here in Santa Fe, so I drove to Santa Rosa, where the wind was. It was clear, but the wind was crazy. So my image is not very good, but I got to do a little interview. This was the only picture I got of the lunar eclipse. This was the next night. This was I was gonna do Bob's thing, but it was cloudy down here that Tuesday night, so no pictures from me. Sorry, Bob. And my latest deep sky photo of the Rosette Nebula. But our buddy Dave Elmore is blowing us away with this image of the dolphin head, and here's some explanation of what we're seeing for the next couple slides. So 3 hours, 12 hours, and then 12 hours processed with 2x drizzle. So here's the 3 hours, 12 hours. That doesn't make much sense. And with the drizzle. And then this next one is of the Flame Nebula and the Horsehead Nebula. He's taken them in not Hubble image colors, but through filters where H alpha is in red, oxygen's in the teal color, sulfur is in the deep red, kind of yellowish area. 9 hours, 30 minutes, and that's what you get. Incredible.
That's amazing.
Agreed. So thank you, Dave. Thank you, everybody who sent in photos. And now it can be a wrap.
Okay. Well, that would be then a wrap. So Zoomers, good night. In here, we'll turn the lights up real quick. We want to just have everybody come up and take a big group photo. And then when we're done with that, we'll put away the chairs and stuff.